Hello and welcome back. This is another ALEKS topic, calculating an equilibrium composition after a prior equilibrium determines K. So really what this is it's two separate problems in one, and we're going to have to be able to sort of figure out what to do in each step and then sort of put it all together. So this is a really nice sort of capstone topic for this equilibrium section. If you can do this type of problem and you understand what's going on at every stage, then I would say you're definitely good to go for your equilibrium section knowledge. So let's go ahead and get started. I'm just going to spend my time on this one topic, one version. It's pretty in-depth, so let's get into it. The first thing that we're going to need to do is come up with a balanced chemical equation on our own. So ALEKS isn't giving us the balanced chemical equation equilibrium reaction to start. We're going to have to sort of read and interpret to figure that out. So it says nitrogen dioxide is one of many oxides that are of interest. It can react with itself to form another form of NOx, dinitrogen tetroxide. So I would start by writing NO2 is in equilibrium, and I guess we could put a phase label on there. Gas is in equilibrium with N2O4 gas. The phase labels aren't super important, but I think it's relevant. So I think putting that in there is good. And now we need to balance chemical reactions. So we're going to need to have a 2 here. When it says it can react with itself to form another form of NO2, that sort of suggests we're going to need 2 of them. But we're going to want to write it like this because it is just one reactant that is reacting with itself to form this dinitrogen tetroxide. So this is our equilibrium reaction. It's balanced. We've got our reactants, we've got our products, so we are good to go for the first part of this reaction. So it says a chemical engineer studying this reaction fills a 100-liter tank with 27 moles of nitrogen dioxide. So I'm going to convert that 27 moles into a molarity, 0.27 molar NO2. That's what we're starting with. So I'm just taking that 27 divided by 100. That would give me my molarity. And so for my ice table, I am going to use molarities for my ice table. I think that it's good practice. Like I said earlier, you don't really need to, but it's just a good practice to always use molarities in your ice table. So that's my initial for NO2. And we have 0 dinitrogen tetroxide. So it says we're just going to put that in, then we're going to do the reaction. And when the mixture has come to equilibrium, then we've got 15 moles left over of my nitrogen dioxide. So my change line is going to be minus 2x plus x. We're going to be shifting this reaction to the right to get to equilibrium. So then my equilibrium line, I can write 0.27 minus 2x, and then just x. And this 15 moles of nitrogen dioxide that's left over, that's my molarity of NO2 at equilibrium. So this 0.15 molarity, just converting that again to molarity, that's what's going to equal, right, this 0.27 minus 2x, that equals 0.15 molar. So I'm going to use this in order to solve for x, so just solving this little equation here for x. I'm going to talk about that just a little bit more in a second. So x we can find is equal to 0.06. So the significance here, just want to be really clear about what's going on in this step. This is our initial concentration. Our change is going to be to the right, so we're subtracting from this side, we're adding to this side. And then here, when I add my I line and my C line, this sort of expression, that represents the concentration at equilibrium. So we're told in this case that the concentration at equilibrium is this 0.15 molar. That's, here, it contains 15 moles of nitrogen dioxide gas at equilibrium. So I can use that in order to solve for x. So we need to be sort of clever about and careful about how we're doing this step. What does this really represent? This represents the amount at equilibrium. What does this really represent? Again, it equals the amount at equilibrium. So just using that to solve for x. Now I can figure out what my concentration of N2O4 is at equilibrium. I could also solve this, right, and figure out, well, I guess we're sort of given here, but I can use that. It will add up essentially to this 0.15. Okay. So that's step 1, and now I have all the information I need in order to solve for a Kc value for step 1. So my Kc is going to be N2O4 over my concentration of NO2 squared. Make sure we don't forget that because we've got a coefficient here of 2. So then I can just go ahead and plug in 0.06 That's my concentration of N2O4 because that's my X value, so we can solve for that. And then 0.15 squared, of course we can't forget that. And then we can calculate a value for our Kc of 2.67. So this is 2.6666. Repeating, we could put in units there if we wanted to, molarity to the -1, not really that important. But this is our Kc value, so this is sort of the first part of this reaction. So using this part here, we're able to solve for the Kc. And then in the second part, this is going to be, how we get to our final answer for our problem. So getting back over here. So for part 2, it says the engineer adds 15 or 14 moles of nitrogen dioxide to this equilibrium mixture. So I'm gonna set up a new reaction over here. 2NO2 gas is in equilibrium with N2O4 gas. And I'm just gonna start a new ice table. Now, for my initial, because we're adding 14 additional moles in, that 14 moles or 0.14 molar, right? It's in this 100 liters, is going to be added to the remaining that I had at equilibrium. So my initial over here is going to be 0.29 molar. So I'm taking this 0.14 plus the 0.15 that was already there from the previous reaction. Now for my N2O4, again, I need to keep in mind what my initial concentration is for the second part of the reaction. It is the ending concentration from the first part of the reaction. So first part of the reaction, we get some amount of N2O4 that's formed. We've got 0.15 molar NO2 that's present at equilibrium. We can use that to calculate my Kc. But then those values, those are sort of being brought over here, and then I'm going to be adding in that 0.14 molar NO2. So definitely confusing. How does this sort of relate to the second part? It's gonna direct what we put in here for our initial concentrations. Our change line is going to be the same, minus 2x plus x. And I know that it's going to be shifting to the right again because this is at equilibrium over here, and then we're adding in more of our reactant. As I add in more of my reactant, well, how's the reaction going to deal with that? It's going to shift to the right to get rid of some of that excess reactant that we've put in there, right, when we add another 14 millimolars or 14 moles. Okay, so then our E line 0.29 minus 2x, and then 0.06 plus x. I can plug this into my equilibrium constant expression now, which we know the value of, right? It's 2.67. So we could write 2.67 is going to equal these equilibrium concentrations, 0.06 plus x over 0.29 minus 2x. This is going to be squared. And now we need to solve for x. So this is where math sort of comes into play now. So we've got this equation here, and it's fairly complicated, and we need to solve this for x. So there's a number of ways to sort of deal with this. If you have a TI-89 calculator, you can actually just plug this in using the solver, and it will solve for x. If you do not have a TI-89 calculator, you can go to this website that's cymath.com, and you can actually just plug this equation, this whole equation, into this website, cymath.com, and it will solve for x. And it will actually walk you through the steps of how to solve for x. So I do think that it's valuable, and I do think that it's important that you would be able to solve this algebraically, that you could write all of this out and use the quadratic formula to solve this exactly for x. But in my class, I'm not going to be asking you to do that. I'm not a math instructor. I feel like that's sort of their job. So here's some ways that you can sort of take this and solve for x. Now, that being said, I do think it's valuable. I agree that we should be able to solve this, algebraically using the quadratic formula and all that to get to our answers. But long story short, 0.0455 molar is the value of x that we're looking for. Like I said, however you end up with that value, that's fine. But we do need to be able to figure out how to do that, right? However you need to do it, depending on your class, you need to figure it out. I will also point out that when you do solve this quadratic formula, you're going to get two different values. And one of those values is going to give you a nonsensical answer. It might be negative, but it also, when you look at the equilibrium expressions, it will give you, if you plug in that x value over here, it will give you a value that doesn't make any sense, right? It will give you an overall negative molarity or something like that. So you're always going to get two values, and you need to be able to decide which of those values is sort of the valid or good value that you're going to use. So in this case, this 0.044 molar, that's the value that we're going to use. Okay, so now what we're looking for is the number of moles of N2O4 at equilibrium, after our second equilibrium. So this calculation here is going to give us our molarity of N2O4 at equilibrium. So we could add these two numbers together. So taking, this right here plus that right there will equal 0.106 molar N2O4. And then I'm going to multiply that by 100 to convert back to moles, because we want our final answer in moles. So multiply that, this is moles per liter, by 100 liters will equal 10.6 moles of N2O4. And then I'm going to take that and just round to 2 sig fig. So my final answer should be 11 moles of N2O4. That's what we are looking for our final answer. And that's it, right? So obviously this is a very involved topic. There's a lot going on. We need to be able to figure out, how to calculate Kc. Really this is two topics in one. So calculate Kc first, and then apply that Kc to our other problem over here. We're going to get to this sort of sticky, icky math situation where we're going to need to solve for x. Being able to write this all out and solve for the quadratic formula using the quadratic formula is definitely very useful. We should be able to do that. And there's shortcut ways. There's other ways that we can do that. I would encourage you to use this website. But yeah, hopefully that is helpful. I will throw in here what you should end up with if you're gonna rearrange this. You should end up with 0 equals 10.667 x squared minus 4.09x plus 0.164. So you can use this is what this should simplify to, and then you would use this with the quadratic formula to do that, which again, you should be able to do that as well. All right, cheers.